Hello guys, in this video I'll be talking about how you code to get the water flow through each pipe and the net flow. So first we'll need some visual descriptions. So to find the flows, we need a drop in pressure over rho plus a change in position and the velocity. V2 squared plus 1 squared, and this will be equal to the negative frictional factor. So if we divide everything by G here, rho G plus C1, so position V squared G is equal to negative F over G, and the frictional force is actually equal to K, negative K plus 4 F L over D V squared over 2G. So we need this flow rate. And this can depend on a Reynolds number here, since Reynolds number is equal to rho VD over mu, which directly relates to this, and the velocity is equal to 4Q over pi d squared. These are all related. Now to go on to code this, so let me get back to code. We're going to need to define a function for Reynolds number. So first thing we're going to do is define, let's see, function RE, that's Reynolds number, ED, and I'm going to go and copy and paste the function. So here it is, and let me indent it properly. So this is an equation for finding the Reynolds number. It has what we need is relative roughness and Reynolds that are going to be provided from them. These values are from the recurring fan friction factor that you can look up on Google. So we got that, and now we're going to have to find a function. First, actually, I need to check this. So actually, let's put some values in. I'm going to use that later for variable. So let me check if this actually works. Shift enter. This is MP is not defined. So let's actually run all the values. And yeah, I believe, actually, let me see. That's right. So now we need to find a function for the flow that finds the flow rate. So define flow. And we're doing this given the K value, the D value, so diameter of the pipe, the length of the pipe, the relative roughness of the pipe, and the delta head of the pipe. Actually, it's not delta head, it's this the flow of the pipe. So the first thing we're going to do, we need velocity. So velocity, we said this earlier, is 4 times Q divided by pi, so pi times d squared. And the Reynolds number is equal to rho times V times D So divided by mu. And now we need to give some variable names here. So row, I believe row for water is 1e to the third. So that's the thing we're using. Mu to 1e to the negative 3. We're going to g of gravity eventually, so equal 0.81. And we're going to want to return the right side of that Reynolds function. So we're going to want to return, let's see, this k, so k for FLD. So we're going to do negative k plus 4, but it's not going to be s since that's what we're doing. So REED times L divided by D. Put this all in parentheses. And that's going to bother me, so let's space. And this is all going to be times V squared divided by 2 divided by G. And shift enter. Actually, this isn't the flow, because we need delta head to calculate the flow. So that was my bad on my part. This should be delta head. So I'll just put delta H actually for short. Enter, put delta H. K value of 1.5. Make it reasonable. 0.1. Length of 1.5. Relative roughness 1e. Negative 3. Q. I might get this wrong. So object H is not callable. Let's think I know what the error is. 4 times F. I believe this is actually, this 4 here should be just dividing by 4. And I got it to work now. So, essentially, let me change that to D head. Because I might have to use, almost for sure, I'm going to use delta head later as a variable. So I'll make sure it works. And now, after we've done that, we can define the flow. So I got a little bit ahead of myself before. So define flow. Then we're going to need D head. We're going to need L, K, D, and relative roughness, I believe. And what we want to find is the resulting flow rate. So let's forget the colon. So right now, yeah, it's not going to do anything. We put nothing in. But we're going to have to find the roots, or the zeros. So we're going to have to make another function. So define flows to 0. I'm going to need in this, just the flow. So that's all we're trying to find. So that's the same thing here. We're going to define velocity and Reynolds number. Except, let's make it big so it doesn't use the same V. And I believe we're going to return the same values. Well, actually, maybe not. Let me put this in and I'll look at it. Actually, we're going to need to add is a delta head. But this isn't defined anywhere, so I believe I made an error. I don't know. This function is going to be called delta head. And control shift enter. And this is what it should give us. So when you do, what should I put in? So F20. I believe I'm going to have to use a Newton function that we're going to have to import in. Even before that, we're going to have to need to specify. So yeah, it gave us an error. It doesn't matter. Let's move the thing up. you're gonna need this specify the delta head 440. L equal 10, D equal 0.5. And we're gonna need to actually have a Q guess function here. Even for the Q guess, let's actually make this consistent with what I put before. I forgot the K value, so we got the Q guess will be equal to P dot high times, so I believe it's the same as this, but it's inside. Actually, we have all that, so let's put it in parentheses. It's gonna be, oh my bad. This is gonna be times. We're gonna take the square root, so sqrt of our negative delta head, so plus 4 times f r e d times L divided by D, and I might have to accept parentheses there, so times 2 times G, so yeah, and actually I forgot the K, I believe it's, I should get rid of this first. Okay, I believe we're taking a guess for an F value. So let's do 0.01, since that's what we used up there. And is this right? So it says we encountered a square root plot problem. This happened because the flow rate was negative, and that means the velocity is also going to be negative, and the Reynolds number is going to be negative, and it's not possible to have a negative Reynolds number. So we're going to have to make probably quite a few adjustments, not just here, but in before, so we can make the Reynolds number positive every single time. And we're also going to have to account for the sign differences that occur. First, let's just see if it works on doing negative. I think I'm going to have to actually import I did have an import Newton up here. So, okay, yeah, so import, and then we're good to go. So we're gonna actually, that's what I have, Newton F to 0, Q, yes, shift enter. This V is not defined, that's my bad, I've never changed it. And it keeps saying V is not defined. Little v. Yeah, I need to change it there. ED is not defined. And I eventually fixed the error of like ED was not defined. So I did that. Yeah, I got this. But that doesn't really solve the problem. So we're going to have to put in NP absolute values and NP signs to change this, so we don't have to manually put in delta head every single time. Then we just do is go back up to D head, and we're going to be np.abs, make sure velocity is negative, and to account for that, we're going to have to add a negative, let's say np, that's big, p.sign q times this. And yeah, the same thing pops up. Now that we have this done, we can actually move this here into this function. Let's end in everything. Actually, let's make some space. And now we're going to actually have a way to find this, but I'm going to explain this in the next video. So